Hello, I'll be presenting my structural analysis of the MORPH-1 wing, part of the MORPH-1 entry vehicle designed for NASA's upcoming interstellar mission in 2075. The MORPH-1 concept addresses a critical challenge, landing on planets with unknown atmospheric conditions. Its telescoping wings deploy mid-entry to adapt to varying aerodynamic environments. My analysis validates whether this wing structure can survive a 10G load during deployment of the full span of the wing. As you can see on the left, the wing uses a NACA 23012 airfoil with a 2-meter cord. The structure is a semi-monocoque design consisting of 5 titanium stringers positioned along the airfoil cross-section. The wing is split into 3 segments, and different stringer stiffnesses are used between the sections to enable the telescoping deployment mechanism. The stringers are made of the titanium alloy with a yield strength of 140 megapascals. The ribs and skin use aluminum 2090 temper 83, and the skin is 2.5 millimeters thick all the way around the wings. At the critical load, the vehicle experiences a 10G deceleration, and this results in a total load of 77.3 kilonewtons at the wing roots. This load combines lift and drag forces acting in the same direction during the entry phase. I used a conservative uniform load distribution across the span, with 80% of the load applied to the forward stringers and 20% of the load applied to the aft stringers, reflecting realistic aerodynamic pressure distribution on the airfoil. My analysis approach comprised of 2 methods. First, I applied the lumped area method for preliminary analysis using the flexure formula. This treats the stringers as discrete point loads and splits the adjacent skin panel areas into the stringers. It provides a baseline stress estimate. Secondly, I performed a finite element analysis validation using PatchRAN. A fixed boundary condition was placed at one end of the wing, simulating the attachment to the fuselage. I evaluated 5 critical failure modes: tensile yield in the lower stringers, compressive yield in the upper stringers, skin panel shear, stringer crippling, and column buckling. Each failure mode was assessed against material allowables to calculate margins of safety. Looking at the stress distributions on the right, you can see the results show peak stress concentrations at the wing root. The table below summarizes the critical FEA results. The FEA method predicted a maximum tensile stress of 157 megapascals and a compressive stress of 158 megapascals. These values were about 15% higher than the lumped area estimates. This difference is expected as the FEA captures the varying stringer stiffness across the 3 wing segments, while the lumped area method just used a uniform geometry for these stringers. Stringer tensile and compressive yield, as well as crippling and buckling stresses, resulted in high margins above 6, while skin panel shear margins resulted in the lowest margin of 2.59. These margins prove that the structure is rated to operate at the initial load estimates. In conclusion, the MORPH-1 wing structure successfully withstands the 10G entry loads with positive margins. The structure has margin for envelope expansion, potentially enabling higher G loads or heavier payloads for future missions. Thank you.